I will be talking about problem archaeological recovery. This is by far the hardest problem of the 46th World Finals. In this problem we have K, which is up to 5 pyramids. And each of these pyramids is effectively a number 1, 2, or 3. And we also have N up to 40 levers. And each of these levers can turn some of these pyramids counterclockwise, which means adding 1 to a number modulo 3, or turn it counterclockwise, which means adding a 2 to the number modulo 3, or not do anything to a given pyramid. We are not actually given those levers. What we are given instead is all the possible outcomes of activating some subset of levers on the initial 0, 0, 0, 0 state of the pyramids. So in particular, if we do not activate any levers, then the state is going to be 0, 0, 0. If we activate some one lever that turns, let's say, the first pyramid counterclockwise, then the state is going to be 2, 0, 0, 0, 0, and so on. We get all the possible 2 to the n states. We are given them as a multiset. Note that while 2 to the n is large enough that it can be reasonably handled, the number of possible states of all the pyramids is 3 to the k, which can be easily represented with k up to 5. This is 243. And given this set of all possible outcomes of activating the levers, we are asked to output any actual description of the levers that matches the provided input. We'll solve this problem in 3 stages. In the first stage, we'll solve it for k equal 1. We'll just understand the one-dimensional case. So in this case, a lever is just one number, 0, 1, or 2. And a pyramid is also one number, 0, 1, or 2. And so the state we are given is basically 3 numbers. How many subsets of levers operating on a 0 end up with 0, how many end up with 1, how many end up with 2. So we end up with, we are given 3 numbers, A, B, and C, the number of 0s, 1s, and 2s that we can get to. And these 3 numbers have to sum up to 2 to the n. And we're asked how many, we're asked to output a set of levers that can generate this output. So let's try to understand how adding a single lever to an existing set of levers actually affects the output. So if we add a lever that corresponding to the number 0, which means a lever that just does nothing, then obviously for any possible outcome, we can achieve it in twice as many ways, because for any set of the previous levers that obtain that outcome, we can either take this lever that doesn't do anything into the set or not. So if we had numbers A, B, and C, then adding a lever which is the value of which is 0 transforms them to values 2A, 2B, and 2C. On the other hand, if we add a lever which, let's say, adds 1 to all the numbers, so 0 transforms to 1, 1 to 2 to 0, then what happens is the numbers change that way. So the new number of ways to get, let's say, 0 is the old number of ways to get 0, because we can just not use the new lever, or plus the old number of ways to get 2, because we can get 2 with the previous levers, add this new lever which adds 1 more, and then we get a 0. And similarly, like B becomes B plus C, and C becomes C plus A. The nice thing to observe about this is that if we don't use any of the 0 levers, what the numbers A, B, and C are always either x and x plus 1, or x plus 1, x plus 1. To begin with, they are just 1, 0, 0, because there's one way to reach the outcome 0 and no way to reach the outcome 1 or 2 if there are no levers at all. And then it's trivial to check that if you apply such an operation, then such a set transforms to such a set transforms to such a set. So this is the form of the numbers A, B, and C always if no 0 levers are used, which means in particular that at least one of these numbers is odd. And notice that adding a 0 lever multiplies all these numbers by 2, which means that we can actually recover, given these numbers, what was the number of 0 levers. It's just the highest power of 2 that divides all 3 of these numbers. So to focus down here, what we have learned is that in a single dimensional version of this problem, we can relatively easily recover the number of levers which don't do anything, which correspond to the number 0. That was phase 1. Okay, now to fully solve that case, I would also need to do something about the 1 and 2 levers, but I am going to stop at this point, and I'm going to proceed to linear algebra or linear geometry, whatever you want to call it. So how do I lift this solution for a one-dimensional case to many dimensions? Well, there is a well-known operation that takes a vector space, because Z3 to the n k is a vector space. And there's a well-known operation that takes a vector space and transforms it just into a line, to 3 numbers in this case. And that's taking the scalar product with something. So we can take any vector x in this space, which corresponds just to a sequence of k zeros, 1 or 2s. And I can take the scalar product with something. And in particular, I can take the scalar product with of all the levers. I can also take the scalar product with all the possible sums, all the possible outcomes that I can get. And taking the linear product is commutative with addition. And so what that means is that if I take all the levers, apply the scalar product, I get I get n numbers, and then I take all the possible sums of that numbers, then this ends up being the same as if I just take the n levers, take all their possible sums, and then to all these sums apply the scalar product. And so that means that I can say, using the exactly same trick as above, how for any given vector x, I can say exactly how many of the levers in the input set will have a scalar product of 0 with that chosen vector x, which here I denote by f of x. I'm saying that the number of, for any vector x, I can find the number of the levers in the set that I'm looking for that have a scalar product 0 with that vector x. Okay, so that effectively means, again speaking in terms of linear algebra, that for any hyperplane, because like what is orthogonal to a single vector is in a hyperplane, for any hyperplane I can determine how many of the vectors, the levers, the vectors I'm searching for lie in that hyperplane. And now how do I get from that into into actually solving the problem, because this is obviously not enough. So the first thing that the thing that I'm going to do is take some subspace of Z3 to the k and sum f of x for over all x of that subspace. So here, this is it. So what does that mean? Well, this is the sum over all possible x in the subspace, sum over all possible j, 1 if the scalar product is 0, and 0 if the scalar product is not 0. And then I reorder the sums. And so this is basically the sum over all possible j, the number of x's in that subspace which are orthogonal to the lever that I'm looking at. And so and this is basically an intersection of two subspaces. The k-1 dimensional subspace of everything that's orthogonal to uj, and the subspace H that I've chosen. So that means that by doing these sums, for, again, any specific subspace, I can determine what is the size of intersection of that subspace with everything that's orthogonal to the vector j. Sorry, I can say how. Yes, I can say I can say what is the sum over all the levers of the size of intersection of the subspace orthogonal to that lever with any chosen linear subspace. So, okay, what do I do with that? Well, the first thing I do with it is I take H to be equal to all the whole space, Z3 to k. And so what is that intersection? Well, if uj is a non-zero vector, meaning it's something else than 0, 0, 0, 0, 0, then this set of vectors orthogonal to uj is a 3 to the k-1 dimensional subspace, and so it contributes 3 to the power of k-1 to the sum. But if any lever is actually constant 0, it's a lever that just does absolutely nothing, then it actually contributes 3 to the k to that sum. So there are only two options, and so looking at what the value of that sum is, I can determine how many contributions of that type I had and how many contributions of that type I had. And so this is the first concrete thing that I actually managed to find out. I managed to find out how many of the levers that I'm searching for are constant 0, are totally no-op levers. Okay, now let's take H to be a subspace of dimension k minus 1. So what does that tell me? Well, I have two subspaces in Z3 of k, and I'm looking through two subspaces of dimension k minus 1. How can they intersect? Well, they can either be equal, or their intersection will be a subspace of dimension k minus 2. These are the only two options. And when do they coincide? They coincide if the vector, the lever uj, happens to be orthogonal to the whole subspace H, which means that H is actually chosen to be the subspace of vectors perpendicular to some y. And then again, I have a contribution of 3 to k minus 1. If uj is not the vector orthogonal to the whole subspace, I get a contribution of 3 to the k minus 2. So I do an ever counting argument, choosing any possible value for that, I choose some vector y, and then for that vector y, I can answer how many of the uj's are orthogonal to the subspace which is orthogonal to H, which is a very complicated way of saying that uj is either y or minus y. So now I've managed to, and I do this for every possible vector y. This might scare you a bit, like when I say things like I am iterating over all the vectors in the subspace. But again, remember the whole space is very small. This is 200 and something numbers. So I can easily afford to do a computation of size 3 to the k for every of the 3 to the k vectors. 3 to k times 3 to 2k is still easily enough to fit into the time limits, because it's still a number roughly on the order of a million. Okay, so now what we have is we have identified a bunch of constant 0 levers, and then we have, for all the other levers, we can say, well, it's either y or minus y for some picked y. And now we have to just pick the signs. So we have to, the situations, for instance, we have some 0 levers, we have some y or minus y lever, maybe you have one more y or minus y lever, then we have a lever which is some z and maybe or minus z, and there's a v or minus v. So, and we have n levers, so we have 2 to the n options, so we can't just check all of them because n is 40, so this is too much. So we have to do something smart to resolve this sign issue, but it seems we are close here, and indeed we are. So the core thing here is to understand, so okay, if I flip the sign on any of these levers, what happens to the sums that I'm given, the sums that I'm operating on? And what actually happens is that if I look at the sums generated by the set of ui, u1 up to un minus 1 and then minus un, so I flip the sign on, let's say, the last lever, this is the set of sums generated by u1 up to un minus un. So I take all the sums that the multiset of the sums that are generated by this set of signs, and if I flip the sign of one lever, what happens is I effectively subtract un from all these sums. The bijection is that the subsets that do not contain un here correspond to the subsets that do contain un here, and vice versa. Yeah. So, okay, so how do I use this to finally solve the problem? I begin by picking any set of signs. So let's say I pick the positive version on all of these vectors, and I check what is the set of sums that I'm going to get for this particular choice of vectors. Now, you might worry again, because it looks like I'm doing something that is size 2 to the n, but really no, this is really something of size n times 3 to the k, because 3 to the k is the size of the the basis of the multiset at every single time, and applying a single lever means to every possible value that I can get, I either add this lever or not add this lever, and then I have a new multiset with a basis of size 3 to the k. So I can actually proceed through this, calculate the multiset of all the sums in time 3 to the k times n roughly. So I calculate this, and I also, for any possible sum that I am achieving, I remember some way of getting there, some subset that drives me to that sum. And now I have to choose some set of UIs. So, okay, I look at this multiset that I have obtained. I might be lucky, I shouldn't count on it, but I might be lucky. It might happen that this multiset that I have in my hands right now happens to be the one that I was given on the input. Ta-da, success, the signs I picked happened to be the right ones. This is very unlikely to happen. So what needs to happen is I need to pick some subset of the levers and flip signs on them in order to get the subset that I'm looking for. This corresponds to subtracting some vector v equal uk1 plus uk2 plus ukl. The levers that I picked, I just subtract this from all the values in the multiset. And I hope, like, I need to pick a vector v, and after I subtract v from all the basis elements of the multiset, I need to get the multiset that I'm given in the input. And how do I find such a v? Well, it's easy. I check all of them, because this is again going to be, I have a multiset of size 3 to the k, I have 3 to the k possible vectors that I can subtract, so I subtract all of them and I check whether any single one of the subtractions that I can do leads me to the multiset that I'm looking for. Now I found a vector that I want to subtract, and now I need to represent this vector as a sum of the input vectors, and to do this I already calculated this, because when I was calculating the multiset, I was also calculating some path to get to any particular basis element of the multiset. So if I can in any way achieve a sum equal v, then it is going to be in my original multiset S. I just look at the cached path to get to this element, and I see it is a subset of levers. I flip the signs on these levers, and this is what I output. So again, to quickly summarize what happened here, I first solved the problem for k equal 1, for the one-dimensional case, and I recovered at least the number of 0 levers in that case. I used that to apply linear algebra and scalar vectors and basically be able to identify the number of 0 vectors in any subspace of the linear subspace of the whole solution space. That gives me effectively for every vector I can tell, for every vector y, I can say how many of the levers are either y or minus y. And then I need to pick the signs, and I notice what is the effect on the multiset of sums on switching the sign on one of the levers, and then I just reconstruct the possible one possible solution. There might be multiple possible solutions, but we are allowed to output any one of them. As the judges, we believed it's a very difficult problem. The contest has not finished when I am speaking this, so I do not know whether it has been solved, but as a judge, I would not be surprised if it went unsolved. Thank you.